All right, everybody. How's everybody doing? How is assignment 2 coming for everybody? Is it going okay? Not going okay. How many people have started assignment 2? Well, that's good. Good. So I was going to say, do not expect it to be like assignment 1 where you can bang it out in the last night and a half. Also, I think as things get closer to the deadline, the machines will start getting a little crowded and may make it work going a little slower. So if you guys can get it done and get it in early, that's probably a good thing. So we handed back the quiz, the so-called quiz 1 with solutions. We definitely encourage everybody to come talk to us if you have questions about those solutions. That is representative of an exam question in previous years. In fact, that was one exam question in previous years, almost verbatim. What else? Assignment 1s should be back probably Tuesday night, I think. And then remember, we're gearing up for our next participation quiz on Thursday. Right. So any questions? Anything to address? Oh, these quizzes are meant to be done completely on your own. They're just meant to force you to think about some of these things. We saw a number of answers that were surprising in how similar they were, and some of you may be getting a little email from me saying, hey, what's going on? So if there was any confusion about whether or not the quizzes could be done as partners, we want you to just sit down in your dorm room in the library, spend 15, 20 minutes banging out, and if you can't get it in 15, 20 minutes, just, that's okay, right? Like the point is for you to get it on the exam, not now. And if you give any effort at all, you're going to give full credit. So make sure you do those on your own, please. Okay, good. So I challenged everybody to think about something last time. And at the end of the CUDA lecture, and oh, by the way, remember we're having a recitation tonight at 7. So Professor Bryant is going to be giving a sort of tutorial on the basic mechanics of CUDA programming at 7 o'clock tonight. So for those of you that really feel like you're struggling to get going with CUDA, I think this will be a great opportunity for you to ask a bunch of questions as well. Okay, so last time we talked about sort of how GPUs worked. We talked about how we write CUDA code for these machines. And it's perfectly reasonable to think about writing a CUDA program in a very data parallel way. I have a kernel. I'm going to map it to this collection. That's not exactly how you write the code, but you can totally think about it that way. Because if I'm going to map this kernel onto all the elements of a collection, which is what you do on computing the inner product in part 1 of assignment 2. And everything just kind of works out because there's this contract between you and the CUDA system that says, hey, as long as I can run the thread blocks in any order that I please, the world is okay. So many times in this class, we've said that thread blocks are independent. And if things are independent, a scheduler can run them in any order, which does make absolute perfect sense. But I put this slide up, here last time. And this is basically, imagine that I'm running this instruction, this atomic add, in a bunch of different thread blocks. And the atomic add is just incrementing a counter, one of 10 counts, making a histogram. So maybe imagine we have a histogram. It has 10 bins in it. I have an array of numbers, an array of integers, maybe millions of numbers. And I break that array up into a bunch of blocks. And I say, for every block, run through your list of numbers and increment the appropriate bins. So in this example, all of the thread blocks are building the same histogram. So they're not independent, right? Like they're not independent. They're working on the same data structure. And I asked the question, was this an okay CUDA program? So who gave this some thought in the time between? So you gave it some thought. And what do you think? Is this an okay CUDA program? Is it correct? Will it terminate? Will it get the right answer? Okay, that's a reasonable answer. We're giving you full credit on a quiz.
But I suspect not.
You suspect not. Okay, so why are you suspecting not?
Because I believe that thread blocks in CUDA are it's the programmer's responsibility to ensure that they're independent.
It's absolutely the programmer's responsibility to make sure that it's okay for them to be scheduled in any order. And making them independent is one way to do that. But in this example, they are not independent. So I'm really asking the question, CUDA is going to, reserves the right to schedule thread blocks in this program in any order. And is that okay? So let's go to the back. Yeah.
Seeing as the add is atomic, so they're not going to interfere, and then the addition itself is associated, then this is okay.
Right, so all I'm doing here is I'm just counting up the number of numbers in every bin. And this integer add is fully commutative and associative. So I can run this code in any order that I please, and I'm still going to get the same answer. And I've put the appropriate mutual exclusion in there to make sure that I don't have any race conditions. But this is an example of a program that can be run in any order, but the thread blocks are not independent in any way, shape, or form. Then I gave you this example here. So this is valid code. Then I gave you a slightly different example where I said, okay, the first thread block is going to say, I'm going to add 1 into this value. And the other block is going to say, while the value, doesn't really need to be an atomic add there, but I did it on purpose for some correctness reasons, which I'm not going to talk about, is while that value, that variable is 0, I'm going to spin. And whenever this thread block sets that value to 1, then I can keep going. So I use the exact same primitive, atomic add. Now, what do you think about this program? Yeah?
Well, unlike normal threads, CUDA thread blocks execution aren't really interleaved. I think it tries to run the 1 all the way through. And so if thread block 1 runs first, it might be blocking thread block 0 for whatever reason.
Right, so what if I run this on a GPU that can run 2 thread blocks at once? Am I okay? Some people are nodding, other people look a little bit unsure. Who's really positive and wants to describe to me why it is okay? But if I can run 2 thread blocks at once, what's going to happen here? Yeah?
Eventually, thread block 1 will add 1, and then, or thread block 0 will add 1, and then thread block 1 will be like, sweet, it's 1, time to go.
Exactly. So what happens if you run this on another GPU that for some reason is much smaller, it can only run 1 thread block at once? And let's say the scheduler decides to do the logical thing and run, like it's got a counter, so it runs thread block 0 before thread block 1. What's going to happen now?
Might it be the case that on thread block 1, the atomic add is atomic, but the comparison is not atomic? So thread block 1 might add 0 to that and retrieve the value 0, but then it will be blocked. Thread block 0 adds 1, and the comparison becomes false. After a while, I guess, compares and continues to execute its internals.
I don't think that can happen here, actually. It's a good point. I never thought about that. But here, if I'm only adding 0, so I'm never going to change the value.
This won't, but maybe it adds 0, reads the value 0, and says, okay, this is true. I can execute. But then after it, makes the comparison, this one.
So if this is 1, if this guy gets a 1 back, that means that this must have happened.
Yeah.
Okay, so what's wrong?
I don't know.
So that's exactly what I want to happen. So imagine we're running on a core with on a machine that can only run 1 thread block at once, and let's say it chooses to run 0 before 1. Am I okay?
0 will never exit because it won't keep on.
Well, 0's got no while loop in there, so 0, it just does its thing. It writes to 1 and it terminates, and then the core loads up this thread block. Then the system loads up this thread block. It says, well, if the value is 1, I'm going to keep going, and it does. That's fine. Now, what if some weird engineer at NVIDIA decided to write a scheduler that said, I can only run 1 at once, but I'm going to run 1 before 0, which is a valid implementation of CUDA, right? What happens now? Yeah, so what's going to happen is that this processor is going to, this thing's going to start running. It's going to spin, and the way we talked about how we're not going to preempt anything here, and so it's just going to always spin because thread block 0 never had the opportunity to run. So I put these examples in here to illustrate how even though most of the time the right way to think about programming in CUDA is to just think about it in a data parallel way. It's the simplest way to think about it. But the system gives you a bunch of synchronization primitives that if you use them, you have to be much more careful. You have to kind of almost think about it like programming a CPU at this point, because you can do things that you that can cause your program to not terminate, which you could not do in a regular data parallel language. And just as an example, I don't want to talk about this too much, this is some code that a lot of fairly elite CUDA programmers write. And this is just the exact same convolve from last lecture. And can anybody, like, if you just ignore my, my text on the right side, if you just look at the code on the left, what is this code doing? Can you tell? It's kind of interesting. Look, like blocks per chip, 16 times 2048 over 128. Like if you look into this code, can you get a sense of what the programmer's trying to do? So if you look at some of the super high performance CUDA code that's written by NVIDIA that they release to the public, sometimes it looks like this, and you're like, what in the world are they thinking? So I'll let you take this offline, but what the programmer's done here is the programmer has written a CUDA program that runs only on, for example, the GTX 980 that we talked about last class. So it creates the exact same number of thread blocks that the programmer happens to know can run on the chip at once. And so it's starting to think about these thread blocks now as like p-threads almost. It spawns exactly the same number of p-threads as thread blocks as he or she knows can run on the chip. And then if you actually look inside of here, there's a global atomic increment, which is when I'm done, while not done, while 1, atomic increment on the work counter, which is give me the next block in the sequence. So the entire distribution of blocks to cores is being done by the application, really thinking about every thread block now as a worker thread. So I'll let you inspect this code a little bit offline, but I've completely flipped the way of thinking about CUDA now from a data parallel model, I'm going to create a bunch of independent work and let the GPU sort it out, to I'm using synchronization primitives to essentially treat thread blocks like threads. There are some times when if you want to implement your own scheduling policy and not use the here built-in scheduling policy in the hardware, that in fact can be advantageous, which is why some people start treating CUDA this way. So CUDA is a very odd programming system in that it gives you all the abstractions to think about it like a big pile of threads, but most of the time the right way to think about it is in a data parallel way. And I think Professor Bryant will sort of talk a little bit about this tonight and sort of encouraging you to think about it in a very data parallel way. Unfortunately or fortunately, depending on how you want to think about it, CUDA gives you the ability to think about it in other ways as well. Okay. So that was sort of a little. Okay, so now you are starting to do, you're working in homework 2, and not soon you'll be working on homework 3. And unlike the first homework, in assignment 2 and assignment 3, you're supposed to write fast code. And so we need to talk about some ideas on how to efficiently write parallel code. And that's one of the things we're going to talk about today. And what we're going to really focus on are balancing these conflicting goals. We would really like to make sure that we take the workload and we spread it out over all of our processors, because there's nothing better we can do than doing useful work all the time on all of our execution units. But in doing so, we need to make sure that we're reducing the communication, the overhead of trying to figure out who should be doing what and when. And sometimes we want to make sure that we don't spend most of our time figuring out how the workers should be doing things instead of doing our actual compute. So back to that example on the first day of class, I remember the 4 students that were up here, they spent a lot of time synchronizing, trying to figure out who was going to take the next pile, and that ended up taking a good fraction of the whole execution time. And that would be unfortunate if we did that in our parallel programs. Okay, so I want to start this lecture with a huge disclaimer. We are going to talk about a progressively more advanced sequence of techniques, because this is a lecture, and if I only told you the simplest thing, that would be a pretty boring lecture. But the number one mistake that most people make is they try and be clever too quickly, especially when optimizing code. It's a program scales if it scales as much as you want it to. Meaning if you are writing a program and you know it needs to run on a laptop or a server with 8 cores or 16 cores, it might be perfectly reasonable for you to adopt an algorithm or a scheduling strategy that works well up to 8 or maybe 16 cores. You do not necessarily need to adopt a more sophisticated method that might work on 1,000,000 cores. And I see a lot of solutions, especially in assignment 2 in this class, where students take a look at the initial starter code and go, okay, I know what's wrong. I know what's wrong. I'm going to immediately jump to the most complicated solution I can possibly think of because it embodies all the great ideas we've talked about so far in the class. Right? And it gets them into trouble really quickly. And that they'll adopt like an asymptotically optimal solution, and sort of the overheads are so high that the simplest thing in the world beats the pants off of their solution. So in general, what you want to be doing is you want to think of the simplest fix, you want to implement it, you want to measure, think about what's actually going on, and then iterate. And that's why assignment 1 in this class was actually all about just thinking about performance. Okay, so imagine I have 4 processors. I have 4 worker threads, each running on a different processor. And I've got this job. I've got a program to do. And ideally, I would like all my processors to be doing work the entire time the program is running. Because if I don't, let's say I give one processor significantly more work, that just means that at the end of the program, these other 3 processors aren't doing anything. And so that means that some fraction of the total work of the program, even though it wasn't inherently sequential, it was running sequentially. Because in this phase, I'm running sequentially at the end of the program's run. And what does that tell me about the maximum speed up that I can achieve? Like what could potentially go wrong if I don't divide the work evenly onto all of my processors or all my work? Am I going to get 4x speed up in this case? Why am I not going to get 4x speed up? Because some part of my code is running with only one processor is doing useful work at some time, and that's going to limit my speed up. So in this case, if processor 4 takes 20% more time than the rest, 20% of the execution time of the parallel program is sequential. I want to point out that that's not 20% or 0.2 in Amdahl's law equation, because that S in Amdahl's law is the fraction of the total work that was sequential. So I need to add up all of these bars and take this percentage over all the bars, just to be clear. Okay, so imagine I gave you a problem, and I said, please divide it equally onto all these processors. What's the simplest thing that you might do? And if somebody says, I'm going to come up with a work-stealing scheduler, I'm going to say that you have made the mistake that I talked about at the beginning of the lecture of let's keep it simple in our first suggestion. So who's got a suggestion? Yeah.
If you have a large amount of data, break up the data evenly among the.
Okay, so if I have n amount of work and I have 4 processors, let's just break it into n over 4 size chunks and parallelize it that way. And absolutely, that sounds like a really reasonable thing to do. In fact, we've actually talked about 2 completely different ways to do that in this class, where in the grid solver example, or in your homework 1 example actually with the Mandelbrot, is we encourage you to think about 2 different ways to break up all the work, where we could break it up into, we could break it up into large chunks, or we could potentially still break it up using a fixed pattern, but we could interleave the rows over the across the processors. So in this class, I'll refer to sort of this strategy of just, before I even run the program, I'm going to come up with a fixed policy of how to assign work to workers as static assignment. Static, we're saying static because it's before the program is running. It doesn't depend at all on any information you get in the data itself. And static doesn't necessarily mean to be at compile time. It could be given n at runtime before we do anything useful. We divide n by 4 in this case, and so on and so on. So here's a question, is when is static assignment a good thing? Or when is it applicable? When should you be thinking, yeah, this is a case, it's super easy. How about I just come up with a solution up front? What needs to be true about your program for this to be the right solution? Yeah.
Each kind of item needs to take the same amount of time.
Okay, so that's a good answer. So what I used here is I used an assumption that every dot on the screen needed the same amount of time to be processed. That's a good point. Did I need that specifically? I used it here, yeah.
Each item must go through the same processing.
That's not necessarily true. It was certainly true of this. And I knew that, and I used that information to come to your conclusion, which was since they did require all the same amount of processing, they all would take the same amount of time. But if I knew that they were all the same amount of time and they did completely different things, I could still make this decision, right?
Not necessarily the same
Okay.
amount of time, but like each, let's say that each item must be multiplied by 2.
Uh-huh.
Say, like so we can be agnostic to the way data is laid out between processes or threads.
Okay, so you're saying in this case, I could kind of make this simplifying assumption that I know that all works the same because I know there wasn't any interesting communication that was going to affect performance. Yeah, I agree with that. Anything else, Isha?
Most of your work is parallelizable, so maybe for some elements you don't need to do some extra sequential work, or maybe overall in the entire data set you don't need to do extra sequential work.
Right, yeah, I mean, so I know, I need to know what's parallelizable. Exactly, I agree. There's nothing that's going to creep up on me. Could I have made a static assignment if, for example, what if I knew that the cost of the work was going to be proportional to like the y axis? Can I? How would you, well, let me say it this differently. Let's say I told you the cost of the work was proportional. Let's say it's linear in the y-axis. How might you come up with a partitioning? Oh, yeah, that's a good answer. Is that, yeah, so you could actually divide it this way instead of that way. And then you're going to make all of the columns equal work. You could also probably figure out a way to divide it into rows still, but they probably would be different sized chunks of the image at that point, right? Yes?
I don't know, take the first row and last row, and then another person.
Yeah, you could, okay, so you could actually say that, you know what, I'm going to give one processor, like a job is not one row, but a job is like the bottom and the top row, and then the next job is like the next one and the next one. Yeah, sure, you could do that. That would mean that you're basically making jobs of equal work again. I've never thought of that one, but yeah, it's true. Okay, any other? So what would you say about, let me go back to my initial question is, when is it, what property of the workload are you using to make one of these good static assignments? So the initial set was that all the work was the same cost, which was actually absolutely true here, but you have been successful in a static assignment when I relaxed that assumption. It's independent, but okay. But what if like, I mean, it could be independent, and maybe like if I start processing this guy right here, maybe it's like if the value is 43, I'm going to loop forever. Yeah.
That you know enough about the data that it can be partitioned evenly?
And by know enough, really what you guys are all saying is that somehow you can predict how much something's going to cost, right? It's very predictable. And for those, you know, some of those changes you made when I gave you a new problem, you were actually kind of restructuring how we partition the code to make the cost predictable, actually. Yeah, so we can, it's absolutely the case is that if the cost is predictable, it would be great if you can come up with a policy ahead of time, because then you don't have to spend any cycles. You don't have to spend any work at runtime trying to figure out that partitioning. So it's like the minimum possible overhead. So the simplest example is exactly what we started with. If all the work is known up front and we know that every job takes the same amount of time, if I have 12 jobs and I have 4 cores, I could easily say, hey, look, you know, I should put 3 jobs on a core. Done. I know I'm going to have a really nice partitioning. Here we have 12 tasks. We know they all have the same cost. We know we have 4 cores. Let's put 3 jobs on a core. What if these bars all had different lengths? But I knew the links up front. The height of the bar is proportional to its runtime, given my diagrams. And so so here it was easy because all jobs had the same cost. Now imagine that the jobs have very different costs, but I gave you their costs up front. Sure, yeah.
The work placement thing is, I believe, an NP-hard problem. So it would make
Yeah.
sense to randomly assign it.
I could, yeah. I mean, it doesn't have to be exactly maximal. But you know, I could imagine, especially if it was a small amount of work, I could just say, you know what? I'm going to assign tasks to cores to make sure that there's roughly equal work per core, and that's how I did it. And if I add up all those bars, look at that. You know, I'm pretty close, and so I have a pretty nice static assignment here as well. So when is this not going to work?
When you don't know the cost to compute certain elements.
When I can't predict how expensive something's going to be, so I need to be more reactive, right? I need to, but many applications where you cannot predict how expensive something is going to be, you sometimes can predict how expensive it's going to be for the foreseeable future. Maybe not for the whole application, but for the foreseeable future. And I'll give you 2 examples actually from scientific computing. So imagine you're doing some large galaxy simulation, and instead of a grid from our previous examples, you have a list of particles, which might represent galaxies or stars or something like that. And you might say, you know what, I want to divide up the stars equally onto the processors. But of course, the whole point of the simulation is that these stars are moving around. And so you'd like to put stars next to each other on the same processor, and you'd like to have roughly the same number of stars per processor. But over time, that assignment is going to change. So, but the universe takes a long time to evolve, and you might be able to run many simulation time steps before your distribution got completely suboptimal. So a reasonable solution might be, you know what, I'm going to divide the stars onto all my processors. I'm going to run the simulation for a while, and then maybe every hour I'll update that partitioning. So it's more or less a static assignment, but sort of on an online scale. Here's another example from a mesh simulation. And typically in these mesh simulations, you might want higher and higher resolution in areas where you care most about the physics or where the forces are highest for stability reasons. And so what you see here in the white is actually an airplane wing. And the mesh is the discretion of the fluid flow around the airplane wing. And you can see that the highest resolution is sitting here right around the boundary with the wing, and as the simulation progresses, the forces might change, and the resolution that we need might change. And so you could easily imagine that the mesh cell distribution onto processors might change over time, perhaps as this ran on a supercomputer over days or weeks or something like that. So this, like I put semi-static on the slide. The terminology doesn't really matter too much, but I just wanted to point out that it's not an either or. I can be conservative and say, you know what, it's going to be fine for a while, so I'll use a simple approach, and I'll just readjust my approach every once in a while. Or we can go all the way and say, look, let's assume nothing about the cost of the individual jobs or tasks, and we'll sort it out as we go. So here's a simple example, and I think you've seen this already. Imagine that we're trying to compute the primality of a whole bunch of numbers, like n is very, very large, millions. And I have a pile of p-threads, and imagine that every p-thread is running this code here. While not done, what is this code doing? Every thread is saying, while we're not done, yeah.
So the code is trying to test the primality of every number up to n.
Yep.
And every thread is like, so you lock on the counter increment, right? So it's basically saying, okay, let's go to the next number and check if it's a prime number.
The next number, right?
Yes.
And really to say next number, I will say every thread is going, well, when I'm done, I'm going to grab the next element in the array that no other thread has started processing yet. And after I get that index, I will perform the primality test, update the output, and then I will repeat until all the numbers are done. So in this code, is it predetermined how expensive every task is, every job is? No, because we don't know how expensive it is to test certain primes. Some primes are much, much quicker to test, right? Is it predetermined how many prime numbers every core is going to get, or every thread is going to get? Also not. So how would you, would you describe this code, if you're describing this code to your friend, how would you do it?
Basically, you have a queue of work, and whenever you're free, you pick the next thing in the queue.
Exactly. This is like there's a big work queue. There's not really a queue, but there's just a big list, and every thread is taking the next item in the queue. And they're all cooperating to make sure that nobody does the same element twice, so we don't skip an element. Good. Yeah, and exactly. So I'd write, if I was to illustrate this code, I might illustrate it like this. We have a bunch of subproblems. In the previous example, computing the primality of a single number was one of those subproblems. It was conceptually as if we threw them all in a work queue, and we had these multiple worker threads all grabbing the next piece of work in the queue. So let's go back to that code. This is the same code for all the threads. What is a potential performance problem with this implementation? Let's say we ran this on a machine, and the prime numbers, let's say the numbers in the list were small, and that you ran this code on 4 cores, and you got like a 2x speedup. What might that be due to? I'm bottlenecked due to this synchronization, right? Because I might have to take the cost of that lock. Or in other words, what is the size of a task in this code?
Smaller than the size of the block.
If the size of, well, first of all, a single task, the way I wrote this here, I would think about it as processing one number, testing the primality of one number. And if testing the primality of one number, the cost of that is low compared to the cost of taking this lock, then the synchronization of just making sure that handling this dynamic assignment is substantial compared to the cost of actually doing useful work. Notice that if I had chosen a static assignment, would I have had to take this lock? No, right? So this lock is overhead that is not in the sequential part of the sequential version of the program. Okay, so this is, like this code has one element of the input, it's one task. We're probably going to get really good workload balance because all the threads are probably just going to be running all the time, taking the next element. But we have the potential for very high synchronization costs if the cost of testing the primes is not that much. And I can illustrate that here, where again, time is vertical, and the blue regions are time a thread is spent doing useful work, and the white regions are time the thread is spending taking the lock, grabbing the next index, performing the atomic increment, and getting out of the lock. So the white regions are time that was not in the sequential program. Yes?
Could it also be a case that suppose you do not know the costs for the individual numbers, but you could run like a simple check, like a simple function which would tell you the cost?
You could do something. You could say, you know what? I am really concerned that most of my time, or a huge part of my time, is spent in these white regions. So why don't I try and gain some information about the size of these tasks? So maybe I run a pre-process to try and estimate. This is a big one. This is a small one. This is a big one. This is a small one. Does anybody else have some ideas on what else we could do to do better? That's a reasonable idea. Okay, so I like that idea. So you could say that instead of saying a task before, every time we synchronize, instead of grabbing one thing to do, we could grab 5. And how would I implement that in this code?
We just have another assign as soon as it grabs that number, it would process the next 5 things and increment the counter by 5.
Okay, so but I have to increment the counter by 5, otherwise I have a problem. Because otherwise then we're doing everybody's doing duplicating work. Yeah, exactly. So we could increment the counter by 5 and then make sure that we process the next 5 numbers here. And in terms of this diagram, how would that diagram change with this new implementation? Right, it's almost like removing the white streaks, or in other words, you could think about it as like enlarging the blue regions because the tasks are longer. Any other ideas? There's one other solution that people often give. Yeah.
Maybe just throw away the lock. It doesn't matter if you do something twice, right? But I don't think it's going to happen very often.
Well, it depends. It depends. Yeah. So the I don't think it's going to happen very often is a little bit. a little dangerous. But, I'm thinking through it in my head, is that if you are taking the lock often, it does mean that we're working on small, easy to determine primes, so the cost of doing them multiple times may be low. So the worst case would be everybody jumps in and everybody grabs a really, really big, hard to determine prime number and spends the next 10 hours working on it. Yeah, so you could say, you know what? The program actually would still be correct if there was no lock here. That's true. I believe that's true. You might duplicate work, but maybe the duplication of work is not as bad as the synchronization overhead. Fair enough. Anything else? One answer that some other students have given is kind of randomize the array and then just statically partition it, so that on average everybody does the same amount of work to eliminate the lock. Yeah. So I like this. I like this answer. It's like so the one simple answer is, you know what? If there's millions of elements, there's no harm to taking 5 or 10 or 20 elements at the same time. That will significantly diminish the overhead of the lock, and is probably the simplest solution in the world here. And so I like that solution. Here we did it by granularity 10. Okay. So how do you know what size these tasks should be? Like I chose 10 here, which was arbitrary. There was nothing scientific about that. But how would you go about trying to figure out what the size should be? So before we answer the question, so what is the reason to have a big task size? A big size, like a large value of granularity here. You guys are answering a lot of questions. I'm going to move on. Yeah, so.
If suppose the log cost was very high, taking the cost of assuming the log is pretty high, so you would want to assume the log very less.
So if a lock is really expensive, or the tasks, the granularity is the cost of any one task is small, then we want to diminish that overhead. What is a reason? So that's a reason to make it bigger. What's a reason to keep it smaller? Why not make the granularity n? Why not make the granularity n? Yeah. Yeah, well, it's certainly not balanced. In fact, the first thread who gets in there is going to take all the work. Right? Exactly. So there's definitely some middle ground, right? It's useful to have many more tasks than processors, because we'd like to be able to balance the work. And I'll come back to that in 1 second. But we'd probably also like to have as few tasks as possible, as long as we stay balanced, so that we minimize overhead, right? And the ideal granularity is going to be based on a lot of program-specific things. But let me give you one example. Imagine that these were the tasks. You don't know these up front, but imagine these were the tasks. Those were the cost of the tasks. And we used our simple work queue example, code from the last slide, to run this program. Does anybody see a problem that might occur? Yeah. Okay, so let's talk through how this is going to happen. So through most of the execution, we're good. Every worker is just taking the next thread, the next task. Every worker is taking the next task. Great. Now we get to one item left in the queue, and some thread goes idle and grabs it. Soon thereafter, the rest of the threads go idle and look to see if there's any work, and they're like, "Oh, great, we're done." And what's going to happen? What's going to happen? Yeah, well, finish it up. And now, so this one thread is going to spend all this time on this last task. And if the length of this task is reasonably large compared to like all the work, the total sum of all the bars, then a lot of my code is going to be sequential, right? And so, in fact, if we assume that distribution, I just parceled these out to the cores, I actually worked it out, and look at that. That's exactly what would happen. Notice that after about half the execution time, the only person that's working is processor 4, or thread 4 here. And we haven't done particularly well. So one answer I was hoping I didn't give away the answer that I was looking for on the slide. I was like, oh no. But no. So one answer, which is on this slide, is maybe we could find a way to chop up these bars into much smaller bars. And if we can do that, then maybe we'll get back to roughly the same task sizes, and we won't have this long pole example. But what if it was impossible to do so? Does anybody have an idea of how you might change your scheduler? Yeah.
Well, like if you know which tasks are going to take the longest, you should do those first so that they can be running on processors while the other guys take the smaller tasks.
Yeah, so if you had any sense of which ones were longer, you could very much take the exact same work queue and just prioritize the longer ones first, and you'd end up with a schedule that looks more like this. So the processor, in this case P4, that got that big task, well, it didn't end up doing very many tasks. It didn't get much done, but still everybody was busy all the time, and we had near perfect workload balance at the end of the program. Just another little strategy for Okay, so we've talked a lot about trying to alleviate contention of that lock, right? That single lock, that single queue that every worker's like, okay, feed me some more, feed me some more, feed me some more. Well, whenever we have contention for something in computer science, a simple example is to start replicating it. And you saw that in the barrier example from 2 lectures ago, actually, when we got around those 3 barriers and turned it into 1. Which actually we never came back and talked to in class, actually. So one answer would be, hey, how about every processor has its own queue of work? So let's say up front, I just partition it statically. And every processor only gets the next job in its own queue. And then only if a core runs out too early, maybe it'll go and hunt around for more work in somebody else's queue. Which has the nice property that for most of the computation, I'm running out of my own data structures, my own local queue, and only at the end, when I would have paid the imbalance problem, do I incur the extra cost of synchronization. And so this is a solution that's very common in a lot of parallel runtimes these days, but it is a little bit more complex to get right. For example, whenever you run out of work, well, which processor are you supposed to steal from? And so on and so on. So before we go any further in this lecture, I wanted to say one more thing, actually. I would like to point out that so far, every example I've given you is here's a work queue, everything's independent. And there's nothing preventing me from saying when I put something in a work queue, that it might depend on previous work in the queue. So I could say, here's a new task, but do not execute me until this previous task is done. And so I've drawn those dependencies here as the red lines. And so the logic in the work queue is going to get a little bit more complex right now. So I'm going to look at the head of the queue. I'm going to see if the head of the queue has any dependencies on anybody that's already running. And if there are, I cannot process it yet. And so actually, in fact, like CUDA's, when you actually call CUDA kernel launch, CUDA kernel launch is actually adding that kernel call into a task queue that is drained by the GPU. So if you launch a kernel and then launch another kernel and then launch another kernel, between the CPU and the GPU, there's actually a queue there. And the GPU is just like saying, okay, give me the next one, give me the next one, give me the next one. You can actually do things like saying, run this, run this, run this, but only run this when this one's done. And so you can actually set up these dependency graphs like that using CUDA. And I'll refer you to the documentation of that. So the summary of this first part of the lecture is we just talked about a number of very basic strategies for when the workload was not balanced well, how to balance it better. So anything you'd want to talk about at this point? Any questions? Because I want to change gears a little bit and go into something a little bit more advanced. This will be a bit of an experiment. Usually, what's about to come is usually lecture 20. Yes?
These workload queues that we have per processor, per thread, it kind of reminded me of the GPU's blocks and like threads running inside the blocks.
Okay.
Is there any GPU workload scheduling that is done per block, like threads inside one block can still work from each other, but since blocks can't communicate, so you assign maybe statically to.
No. I do want to point out, though, that the way a GPU handles the blocks is very much like the work queue strategy that we just talked about. So that's scheduling the blocks in a launch and not the actual threads in a block. Because remember we said, okay, imagine we had 2 cores. That's like having 2 workers. When the CPU says execute this kernel and do 1,000 blocks of it, then we have a scheduler in the GPU saying, here you go, here you go, here you go, here you go, until all 1,000 of them are done in this case. So what we just talked about in terms of scheduling a task queue, what would you say that the GPU is using a dynamic scheduling policy or a static scheduling policy to assign thread blocks or to map thread blocks onto the GPU's cores? Dynamic. What would you say that ISPC is doing to map tasks to a CPU set of cores? Okay, so we have a vote for static. Okay, so who thinks it's static assignment for ISPC tasks to CPU cores? Okay, you may be in the minority, unfortunately, but oh, 2. So who thinks it's dynamic? So everybody else. So somebody stand up and tell me why you think it's dynamic. I want to hear an answer here.
Well, I think like ISPC tasks have like an interface to hardware threads. So the scheduler can basically say like, here, I'm going to put this task on this thread, this other task on this thread. So they can make that dynamic decision when they're running.
And how do you think they make that dynamic decision?
I don't know. Probably like work like the size of maybe the number of items in the task.
Remember the keep things simple argument on slide 1. I can guarantee you, actually, if you look at your assignment 1 code base and you go look in common/tasksys.cpp, you will see something that looks exactly like this, where if this while loop is being run by all the threads that are created on the machine, and just remove test primality with a function call to your ISPC gang launch right there. So they take the simplest possible solution, which is we're going to assume that this programmer gave me tasks that were big enough so that taking this lock is not that big of a deal. And I don't think you ever really observed in assignment 1 the ability to make tasks too small. I think we asked you in problem 3 to like create, pick an optimal number of tasks, and people were saying, well, I went all the way up to 1 task per row of the image, and it still seemed fine. Things were still going well. And that's because, well, this probably won't be a lock in the actual implementation. It's probably just an atomic increment. That atomic increment, that overhead, is pretty low compared to the cost of computing Mandelbrot for the entire row of a 1024 or whatever size it was image. I imagine if you made the tasks like process 1 pixel in ISPC, you probably could have observed a slowdown due to the overhead of dynamically assigning all these tasks. And it's something I encourage you to maybe hack up. And if you can see that, why don't you post it on Piazza? Because I'd be interested to know at what size do we really start to see the effect of task overhead, or dynamic overhead really starting to get to you. But yeah, I mean, this doesn't necessarily need to be a lock. This could be an atomic increment instruction on a modern PC. It's going to be pretty lightweight. Good question.
Static?
Oh yeah, so why static? Sorry?
It seemed like when one instruction stream is running, let's say that there's an if case, there's an if-else branch,
Yep.
and then the if case ran, and then one of the program instances stopped and wait, and then the else case ran.
But my question was referring to how it schedules tasks, not how it schedules the program instances within a task. So the program instances are absolutely statically mapped to the vector instruction lanes or elements in the vectors. That is absolutely a static mapping, because it would be very expensive at that small granularity to do a dynamic mapping. But at the granularity of these big tasks, the system has chosen a dynamic mapping because in most likelihood, as you all saw, the overhead was low and that it's great to have the flexibility because it's really hard to predict how expensive those things are going to be. So that's a good example of a different solution for a different part of a program, exactly. Yep. So you're right that that was static, but that was a slightly different effect than what I was asking about. Okay, so I would like to talk early on in the class. Usually we do this lecture later on. But in the last 30 minutes, I'd like to talk about, we've talked a whole lot about parallelism where it was, here's a list of things, and let's map a kernel onto that stream. And that computational pattern, that's representative of a lot of simple programs, but there's a lot of other programs in the world that don't match that structure. So just to recap, everything that we've kind of talked about so far in class has been, for each element of array, do this. For every task, do that. Every task, do that. For every thread block, run this kernel. 210, map this collection, map this kernel or function onto this collection. And we haven't really talked at all about OpenMP, but if you wanted to get parallelism in a for loop in C, the easiest thing to do would be for in a modern compiler, just wrap this Pragma OpenMP parallel for around your for loop, which will tell GCC or ICC or Clang, hey, look, trust me, these are independent. Spawn a bunch of P threads to run these iterations in parallel. And all of those can be thought of as, here's a collection. I'm going to map a particular function onto that collection. And we also thought, okay, so that was one way of thinking about it. And the other way we've thought about kind of doing the same stuff was, well, maybe I'll have this collection and I'm going to create, a P thread per core. I'm going to divide the work in that collection up amongst the threads, whether it be static or dynamic or whatnot. And all the threads will just do their job. And you can do that with P threads. But I want to talk about, a very different style of program these days, and Quicksort might be a canonical example of that. Everybody's seen Quicksort, right? Many, many times. So here's a very simple Quicksort. You might want to get up to speed on it because this will be the running example for the next 25 minutes. And so Quicksort is, well, if we're, if we have a singleton element, we're done, or if we have, just to review. If I have a collection, I'm going to find a pivot. I'm going to partition elements to the left or the right of the pivot. And then I'm going to recurse by sorting each of those subregions to the left and the right in the pivot independently. So first of all, where is the parallelism in this code? Where's the most obvious parallelism in this code? First step in any programs we look at, we say, okay, where's the stuff that can be done independently? Certainly the two recursive calls are on independent, completely disjoint sections of the array, and they can be actually performed independently. Good. And how much parallelism is in there in this program? Is this a program that's only going to be able to make use of two processors? You say no, but I only see two parallel things here.
So as you keep going down into the function, you get more and more parallelism, more and more chunks.
Exactly. So the parallelism, the independent work reveals itself recursively. Unlike this parallel for all, where we say, here's a million independent things, here the program is like, here's two things, and each of them create two independent things, and each of them create two independent things. And not too long, we're going to have a bunch of parallel work to fill up a machine, right? So if I wanted to look at the dependencies amongst each of the calls to Quicksort, it might look like this tree here. So everybody, this is good, right? Nothing, no rocket science yet in the lecture. Okay, so how would you write this program with I wouldn't really want to write this program with a for all loop, right? Like for all, for I equals 0 to 2. I'm not either sometimes, it's all right. So we probably like to have some other programming abstractions that more echo the way we think about this problem, right? Like the way I'm thinking about it, if I looked at this, I said, okay, I want you to partition the work, and then after you partition the work, I want you to do this thing and this thing in parallel. And so I'm going to give you some code examples in a language, I wouldn't really even call it a language, but a set of C extensions called Silk that allow you to make function calls asynchronous. So if we normally call a function, what happens? Somebody give me a description of what happens if we call a function. I'm running a thread of control. I call the function foo.
stack, and then you start running that function.
Sure, I mean, control for that thread of control moves into the function, we execute the function, we return, and then we resume in the caller, right? Sequential set of operations. So Silk has a function call, but you can put in front of it Silk spawn foo. So what Silk spawn means is that we need to invoke the function foo, but unlike a normal function call, the caller can continue executing asynchronously with the function foo. Can. Not necessarily will, but can. So it would be perfectly valid to say spawn foo, some thread starts running foo, and the caller just keeps running past that completely in parallel. And then, of course, to sync everything back up, there's one other primitive called silk sync, which says wait in the caller until all asynchronously spawned child function calls have completed. So I might be like spawn foo, 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 do whatever I'm supposed to do for a while, and then sync, and that means I'm going to wait. I'll be guaranteed that all those foos have completed when I get to the end of the sync. Okay. Right, so this is very much like a fork, logically create a new thread of control to handle this function. This is very much like a join, which is wait for all of these independent threads of control to complete, and I want to know that before I continue on. So the spawn and sync, does that make sense? Has anybody used Silk before? You might have used Silk in 2.10, actually. Hey, Brian's used Silk. Silk's very, very elegant, actually. Very, very elegant. So just to make sure to check your understanding here, I have a couple of different Silk programs. And what I'm drawing here is I'm drawing sort of the logical threads of independent threads of control, and I'm drawing their sync points as these nodes. So I'm showing you the point at which it forks off, and I'm showing you the point at which it comes back and syncs. So here we have Silk spawn foo, bar sync. Well, look, so we have the main thread spawns off foo, continues on, executes bar like a normal function call. So the bar might be done in parallel with the foo, and then the calling thread syncs back up, waiting for the end of foo. Silk spawn foo, silk spawn bar, silk sync is the same amount of parallelism, but actually note that it creates two asynchronous logical threads of control. It says spawn off foo, do it asynchronously, spawn off bar, do it asynchronously. The calling thread doesn't really do anything else, it just sits there and waits for both of those. So these are two different programs, even though both of them are ways to express code where foo and bar are run potentially in parallel. And just to kind of push it, foo bar fizz, buzz silk sync. Buzz is called as a normal function call in the caller thread. And you'll notice that foo, bar, and fizz are all asynchronous calls, and that's what's reflected right here. And then the caller joins on fizz, bar, and foo. Yes?
How is this different from me creating manual threads, executing them, and then joining them after I complete?
So here's an interesting question back at you. Are you asking me about the implementation, or are you asking me about the abstraction? The abstraction is exactly what I just said it is. And that's very different for a pthread. A pthread says, well, you could almost say that silk spawn foo has almost the same semantics as pthread create, where foo is the call. But implementation,
Silk have like workers that are waiting.
yeah, so that's where we're going. In fact, actually, I take back what I just said. You could say you could think about implementing silk spawn foo in that way. But a pthread create really means something. It says create the execution context for that thread and start running foo. Here, that's not what this is saying. This is saying, I would like you to logically run foo asynchronously, concurrently with the calling thread. I will not tell you if you're actually going to run it in parallel or not. The system has the opportunity to make that decision. I could easily have implemented this code and have a correct Silk program by just alighting all of the spawn and sync keywords and just running the code as normal. That's a valid program. That would not be a valid interpretation of a pthread. People would be like, what the heck? Yeah.
We also have additional control over the sync. Like you should only wait for foo and bar, and the fizz can keep on going.
No. I mean, maybe there's some exotic extra features of silk these days, but in sort of the pure silk in which I want to think about it, no, let's just say that you wait for all of your colors. Somebody might correct me on that because there may be in the actual modern GCC implementation of this, there might be, but conceptually, no, let's think about it. And there's also, I should point out, that there's an implicit silk sync at the end of any function. So if the caller just returns, you can think about it as syncing on everything that it created before it returns. There's not going to be all these dangling calls. Okay. So I'm glad you asked that question because I did want to point out on this next slide that notice that silk spawn does not specify how or when parallelism will occur, when we're going to schedule these things. It only says that you may, if you so wish, run this concurrently with the calling thread. Silk sync does serve as a constraint on scheduling, which says, hey, you better finish everything that you have spawned up until this point before you let me to continue on. So let's look at quicksort as implemented in Silk. And so it looks awfully like what you'd expect, which is ignore the top if statement and just say, look, we're going to partition the array. We're going to silk spawn the first half. And we could have spawned the second half, but we just call the second half in the normal, in the current thread of control. And what I'm showing here is the graph, the dependency graph that arises from this. Top level, we're going to do one call to partition. Then we're going to spawn off a quicksort here. We're going to continue on here. And each of them are going to recursively start spawning off more and more work. So the dependencies between all of these programs, or these logical threads, is shown in this diagram. Does anybody know why I have this if begin is greater than n minus cutoff? Just sort the thing? Yeah. Yeah, at some point there's going to be some synchronization and trying to coordinate all these parallel threads when I get into the implementation. If this is just a small number if the size of the array is small enough, it makes sense to just do it in a single thread, do it sequentially. Because presumably we've already got tons of work because we've recursed a bunch of times. We might have already made hundreds of thousands of jobs on sections of the array. The difference between making hundreds of thousands of jobs and making millions of jobs probably isn't very helpful. And in fact, it's probably detrimental to performance. Good. Yep. Right. So that's exactly what you said. We're just going to sort sequentially if the problem size is sufficiently small. So when you're writing a Silk program, your job as the programmer is, I'm just going to hand the system independent work, parallel work, or potentially parallel work. And I'm going to trust that Silk's going to do a good job of making sure all of my cores are busy. Now, you need to help by giving the program, the system, enough work. If you give it 2 pieces of parallel work and say, I want good performance on an 8-core processor, there's going to be a problem. If you give it 1,000,000 pieces of work, of which each of them are sort 2 numbers, there's also going to be a problem because it's going to be managing all the queues and things like that. And so a good rule of thumb, actually, that a lot of people use these days is that a small integer, 8, 10, 6, a small integer, you want to create as many jobs as a small multiple of the number of cores in your machine. So for example, if you created 8 times as many jobs as the cores in the machine, that means that every processor is doing on average 8 things. And that means that any one processor, if you get out of balance, is only 12% of the total runtime. So hopefully you're not going to get a really long task like what we showed in the earlier part of the lecture. Okay. So let's consider this now we're going to implement a Silk scheduler. And I want you to consider a very, very simple Silk scheduler. We are going to create a pthread for every single time. We're going to go with the logical implementation, the simple implementation. We're going to create a pthread for every single spawn. And we're going to translate sync into join. What might be the problem with the performance of this runtime? And think back to that demo I showed you in class about 2 classes ago, where I showed you that I could take the next task out of a queue about 100,000 times faster than I could spawn a pthread.
There's a lot of overhead in a pthread.
Yeah, there's a lot of overhead in a pthread, so that cutoff that I make in my program better be really freaking big for this to actually be a good solution to the problem. Exactly. Right, so we're going to create all these threads. We might create many more threads than processors. We might create hundreds of thousands of threads, and we're punting it to the operating system to sort of sort it all out, which is probably not the best thing. So we're going to do what you all now know how to do. Is our runtime is just going to spawn up a thread per core, per execution context. If I have an 8-core machine, maybe I create 8 of these threads. And all of these threads are going to basically be, while not done, give me the next thing. While not done, give me the next thing, and so on, and so on, and so on. Yep. Yeah, all right. So let's think about this simple code. Silk spawn foo bar silk sync. All right. So I want you to consider, and so I'm going to call the thread, the thread that we create with the spawn, I'm going to call it the child thread, which makes sense. It's the child call in the tree. And I'm going to call everything else on the caller thread the continuation, which means if the caller continues on, it will run this. So in this case, we kind of have an option here now. Imagine we only have one processor. We have an option. We can immediately run foo, or we can continue on and run bar up until the next sync. And when we get to the sync, we could then go run foo, and everything would be fine, right? So we have this question of like, what threads should execute the child, and what thread should execute the continuation. So imagine we have 2 threads. How would you do it? Let's say the worker pulls 2 threads. Let's say both of them are idle. Completely idle when we get right to this silk spawn foo. How would you handle this situation? I'm going to go somewhere else. How would you handle the situation? Can someone come up with a scheduling algorithm for me that gives you the performance characteristics that you'd like? So what are the options? One option is I can ignore the spawn and the sync, and I can just run it all in one thread, just like a normal function call. It's correct. What if the other core was busy doing something else in the program already? Then what I just said actually isn't such a bad solution, right? But let's say both of these cores are idle. Both of these worker threads are idle. So there's only 2 options here. I can run foo on the caller thread and continue on with bar, and push the bar to somebody else. I could run bar on the caller thread, push foo to someone else. What does anybody care? Yeah, there's not a right answer to this question, but
Let's say foo and bar work on the same data.
they're independent though.
Yeah,
Okay. They can be run. They can certainly be run concurrently because that's the promise of sync. Yeah.
But they're operating on the same initial set of data.
Oh, I see. Yeah.
That may, scheduling them on the same thread may give us like cache locality.
That's true. You could say that screw parallelism. I'm going to ignore the other processor completely, and I'm going to run both here. Okay. But, at some point we'd like some parallelism, right? So yeah, I mean, that's a very valid concern. I think if foo and bar were these big complex functions, I think I'd probably want to get some parallelism at some point out of them. Anybody have any opinion? Yeah. Yeah, so you're just saying like keep going because I already have that execution context set up. That's great. And somehow I'll push foo off to the other guy. And I can imagine somebody making another argument for the other direction. There's nothing really fundamental yet about this. Okay. So one thing we can do is we could say that the thread runs foo, then returns from foo. So let's say like I have this decision. I'm like let me go back to this example where the other thread is busy. So imagine if I just say, hey, the other thread's busy. There's nothing for him to help me with. I'm just going to call foo normally, and in the middle while I'm running foo, the other thread goes idle. So we've lost a big opportunity here because the other thread should have been something like, you know what, I'm done. Maybe I should go work on bar. That's what we'd like to happen. So the way these systems are going to work is that whenever you get to one of these sync points, I'm going to put either the continuation or the child into a work queue here. In this case, I put bar into the work queue, and I continued working on foo. And so that in the future, or if the thread 1 starts off as idle, it can look around and say, hey, I need something to do. Oh, look, thread 0's work queue has something in it. Let me go grab that, and I'll start working on bar. So thread 1 has stolen bar away from thread 0, which was currently busy working on foo. And then thread 1 can keep going working on bar. Good. So we have some options now. So that's the basics of a steal. So we know we have to kind of put a record of here's something to do in a queue. And the other thread's going to come over at some point when they're idle and take some of that work away. But we do have some, so one answer is we could run the continuation first. And we can put foo up in the queue. Or we could run the child first. We could run foo, and we can put bar up in the queue. Okay, so which implementation do we choose? So take a look at this code here. For I equals 0 to n, spawn foo, sync. So what did I just do here is I actually just kind of wrote a data parallel program in a way. I said for every element, it can be done independently. Let me go ahead and reveal all of that parallelism to the system. But look what's happened if we end up running the continuation first. So if we run the continuation first, the original thread 0, is going to keep pushing spawn foo I, so foo 0, spawn foo 1, spawn foo 2 onto this queue to reveal it as parallel work. And then it's going to get to the very end and want to start processing its queue. So does everybody see how so we're running the continuation first, which means we're just going to keep running through the the for loop, creating and revealing more parallel work into the system. And you can see if n equals 1,000,000, I just created a queue with 1,000,000 deep. But now there's plenty of work in the system for someone to steal. Okay, the other way I can do things, let's think about how if I do it the other way. Imagine what I do is I put the continuation in the queue, and I start running foo sub 0. Then the other guy, so the queue now says, look, the continuation is there with the value of I 0. And so thread 0 is going to, the other thread's going to come along and steal that, and it will execute the next iteration of the loop and start working on foo 1. And then put the continuation in its queue saying, look, someone needs to keep going from I equals 1. And you can imagine that the continuation is going to kind of bounce back and forth between the processors as they get done with all of these foos. But I didn't create a queue with 1,000,000 elements in the system. So in one case, I exposed a bunch of work all in the same thread. And the other thread probably would have stolen foo 0, and then foo 1, and then foo 2. Here, the continuation bounced back and forth. So I had a lot of communication, but I didn't explode the system into a lot of different queue elements. So if we do this with quicksort, okay, so imagine that I run the child first. And if you think through this, what's going to happen is imagine I run quicksort on 200 elements. I'm going to break it into 0 to 100, 100 to 200. I'm going to push that onto the queue and work on 0 to 100. Then I'm going to push 50 to 100 under the queue and work on the recursive call to 0 to 50. And I'm going to keep doing that and see how you can see how now I'm working on 0 to 25. I'm always taking the left branch. And I've pushed the right branches onto the queue. So the queue has 3 elements in it. And now all the rest of these processors are completely idle. Now they have an option of what work they should do. There's 3 options. They could steal this job, they could steal this job, or they could steal this job, right? So which job should we steal? So let's just take one of the 2 options. Who thinks that we should steal this? Who thinks we could steal this? And I bet you could come up with good arguments for either way. No. So you're going to choose to steal 101 to 200. Why is that? Locality. And what do you mean by locality? Because I would actually think that we just partitioned 0 to 50. So this was the last data touched by the processor. There's a lot of answers here. We'll go in front to back order, I guess. Yeah.
Sure. So I would steal the thing from the top of the queue.
So you're also going to steal the thing from the top of the queue. And what is your reason the same?
No. You
No.
don't have to shuffle everything in the queue around, so you don't have to move. You know, like you don't have to shift elements down.
Oh, yeah, that's true. I could imagine a smart queue that didn't shift everything around. But okay, so that's any other reasons? Yeah, go ahead.
My idea is if you steal the biggest one,
Uh-huh.
then you can spawn a whole bunch of them.
I like that, right? So it makes sense that if we're going to I haven't told you how we're going to do it, but if we're going to go steal this guy, grab this out of this data structure, move it somewhere else, steal it, it makes sense that we would steal a huge amount of work so that we don't have to do a steal again for a while, right? And so nicely, if this is a divide and conquer algorithm, the biggest pieces of work are going to be at the top of the queue. And moreover, I like that answer of locality, but I actually would conclude it's the opposite, is that this processor's already just worked on these parts of the array. So it makes sense that it's probably sitting here in this thread's L1 cache or something like this. So you get maximum locality if this guy reads from here and somebody else steals from here. So the way this is going to work as we're getting towards is, hey, look, when this guy runs out of work, it's going to look at the bottom of its queue, because that's the most recent data that it touched, and it's a job that's already sitting there. If you ever run out of work, you're going to go look at somebody else's queue, and you're going to take the top element of it, because it's the oldest data as well as the most data. And so you can amortize any cost of the steal over this large operation. So here in this case, we're going to steal, so thread 2, let's say, stole the top, and then thread 1 stole the next biggest thing that it could have stolen. I probably should flip those around. And that's exactly how it's going to work out, right? And then these guys are just going to keep pushing work onto their stacks, and so on and so on and so on. And there's not going to be any stealing that needs to happen until somebody runs out of work again, which might be for a while because we stole the biggest possible job that we could get. So this suggests, if things work this way, this actually suggests that I just wrote a really, really terrible Silk program, actually. Because no matter how my quick select program is a great program, my for loop program is terrible. Because the only two options, if I run the child or I run the continuation, I reveal the parallelism sequentially. So if I always ran the continuation, that single thread is going, here's a foo0, here's foo1, here's foo2, here's foo3, here's foo4, completely sequentially, and I'm blowing all this space in my queue on these tiny little jobs. Conversely, if we did it the other way and we said, okay, I'll work on foo0, you go steal, then the other guy creates foo1, and then it bounces back and so on and so on. It's still sequential, but with a bunch of communication. And that's why actually Silk has Silk has a for all loop in it, but Silk's for all loop is actually implemented as this recursive process, which says, look, if there's n iterations, spawn the first half and the second half, and then recurse, so that we can very quickly generate the parallel work on different threads. It also avoids this explosion of a bunch of little jobs in the queue. Right. So the code at write generates work in a bunch of little work in parallel. A lot of work, big jobs in parallel. The code at write generates a whole bunch of little jobs sequentially. Okay, so the only thing I haven't told you how to do is how we're going to handle the sync at the end. So now we know how to just, whenever we spawn, we just shove stuff in our queue. If we ever run out of work, we pull something out of the top of somebody else's queue. But sync is a little bit complicated. How do I know when everybody that got spawned, this whole tree of work that might be done by totally different processors, how do I know when it's done? Okay. So let's work through this very, very simply. I'm going to go back to my simple example. So imagine that we get to the end of this program, and everybody's doing their job. The continuation is here at I equals 10. And I need to know, I can't move this thread, if it finishes that loop, it cannot move past that Silk sync until all of these foos have finished working, right? That's the rule. So let's think about how we do this if, for some reason, none of the work generated in this for loop was ever stolen. So there are no other processors working on any of the jobs in this block, which I'm labeling block A. Let's say that every time we push something onto the queue, this thread ended up consuming it. So we're sitting here, we're almost done, and oh no, sorry, this should be continuation I equals 10. So if nobody else has stolen anything, how do I implement sync?
You can push a marker like or something onto the queue, such that when the thread pulls that down, it knows that it's done. And keep going.
Good, but in this case, nobody's stolen anything. So sync is supposed to wait for all other threads that have stolen work. It's actually even simpler.
Well, it doesn't have to wait, right? 'Cause it can
Yeah, exactly. It's exactly the same as any serial execution. So if there hasn't been anything stolen, sync is just a no-op. So now let's think through the case that let me jump to here. Okay, so let's think through the case where I want to move to just the very end. We can do most of this. Okay, so now no, I can't jump through all that. That's not going to work. Okay. So now let's think through really quickly a case where thread 1 has stolen some work. So thread 1's doing its job. Sorry, thread 0 is doing its job. Thread 1 runs out of work and steals the continuation from thread 0. So what we're going to do is we're going to do exactly what you said. We're going to make a note. Hey, look, this has been stolen. It was stolen. So one guy is running foo. One thread is running foo. So I say one active worker, and none of them have finished yet. So I just bookkeep it like exactly what you said. And then thread 1 starts to do its job. So it starts doing work. It starts working on foo1, and it makes a note. There's 2 active workers, and none of them have finished yet. And so we can continue to do this, over and over and over. 3 active workers. And at this point, we have 3 active workers, but thread 0 has finished foo0 at this time. So a really simple implementation would be for thread 0 to wait until the number of done workers equals the number of spawned workers. You could just sit there and wait. So let's just let this thing go idle, and this will continue over and over and over until we get to, let's say, spawn 10, done 9. And then as soon as this becomes 10, thread 0 can continue on in the caller and do its job. So we're done, and we can move past and start working on bar. So I'll stop there, and I'll go over a little bit more advanced version of this because it was an experimental lecture, so I went over a little bit. But you can see how it's actually quite simple to schedule all these things. Okay, I'll stop there, and we'll talk some more next time.